James, the stage is yours.
Well, thank you very much for the introduction, and I'd like to thank you all for for being here today, and especially to the organizers for this invitation to speak to you today. So for today, this is basically a talk in 3 parts. So first of all, I want to introduce who we are, and then I'll discuss a lot of the research we've been doing lately on our development of our FSI, and then I'll conclude with some of the development we've been doing on our in-house post-processor. So the aim for this talk then is to show our capabilities and how we are becoming compatible with open source and how we're utilizing the power of OpenRadioss within our own development. And again, at the third part of the talk, how we're planning on giving back to the community. So first of all, who are we? In general, we are a software engineering and consultancy firm. Our focus is historically and typically in the areas of blast, shock, and generally weapons effects. And right now, our primary software that we develop and sell is a CFD tool called VIPER Blast, which is an air blast code. But in very general, because we do both consulting and software development, we get this nice feedback loop where we talk to our clients, they tell us what else they need, then we can develop it into our code, and it's just keeps improving our software capabilities and our consulting abilities. So we are available for both aspects in a wide range of weapons effects and so forth. And right now, the primary software we sell is VIPER Blast. And if you want a demonstration, please see one of us either throughout today or during the Silos conference, and we'll be happy to give you a demonstration. We also have an in-house post-processor called Sidewinder that, again, I'll be discussing in quite a bit of detail later on today. A fluid structure interaction solver, which is in the alpha release. And then we also have some other software development in progress, including a building damage estimator and an underwater explosion calculator and an underwater explosion CFD code. So we do have a lot of software within development, as well as some software that is publicly or that is available for use and purchase. We also have a lot of clients who either have purchased our software or we consult with, and this is just a handful of them. And you can see that we do consult with industry, with universities, as well as governments. So we do have quite a variety of clients across a lot of ranges of industry, as well as across the planet. So we are out there quite a bit. So a brief overview of our primary software. I know it's not necessarily the focus of this audience, but it is still a good background of what we do, and it might actually be something that will be useful to some of your own research. So it is a computational fluid dynamics code. It's mainly designed for the simulation of blast, but it can also be used for understanding how blast interacts with very complex geometries. So here we're showing the blast through a city. I asked earlier today what it was. I think it's Bristol. We also have a nice example where we blow up Dublin. But as an even nicer part, for example, if you want the complex geometry, you can just go in, you can pull in your favorite city, put in a bomb and blow that up yourself. So you're not just limited to what we want you to blow up. You can blow up anything of your own choice. But we also have a range of ways you can blow up stuff. So we can do with deflagration, detonation of vapors. And on the next slide, I'll show you that we also have a lot of explosive materials itself. Now, one of the main selling features of our code is that this runs on the GPU. So it is very, very fast, and it's typically faster than most of the codes otherwise available. It also means that a lot of this stuff can be run on the laptop. So you'll see my colleague at the back has a nice PowerPoint on his computer, but that's the exact same computer where we do a lot of our simulation work. It also has a very nice and interactive GUI to make this a very, very nice user experience. So you don't need to be an expert in computers or computer software to be able to use it and get really useful results. It's also a very, very interactive workflow. And again, if you want to see a demonstration of that, please feel free to see one of us. So just quick numerical, because this is a good audience for that. Finite volume in viscous Euler solver. We use the AUSMDV numerical scheme, Muskell-Hancock time limited, second order in space and time. And again, because this is on the GPU, we can easily handle dozens or hundreds of millions of cells, and it can run in a reasonable time period. We also have inbuilt a selection of explosives you can use. And as you can see here, it's the same simulation, but just two different explosive materials, and the results are already quite varying. So you can either use some of our own built-in explosives, or if you have your own bespoke explosive, you can put in those properties, model that yourself, and those properties remain just within your own input deck, so they remain bespoke and private to your own company if security is an issue with that. So we have, this code has been available for a while now, and we have done a lot of verification with it. So here is a vented chamber, and we can see that our experimental or our numerical data does a very good job at reproducing the numerical results. And here we have an explosion in a confined container. And again, we do quite well in reproducing the numerical or the experimental results. So we do have a lot of other B&V that is available, and again, we do tend to do quite well in reproducing the experimental results, in some cases even better than our competitors. So that means we have more accuracy and faster results in a lot of cases. So I know this audience is typically a little bit more interested in the structure and capabilities with OpenRadioss. So for the next section of the talk, I'm going to focus on a lot of the research I've been doing over the past, a lot of the development I've been doing over the past year and a half, 2 years, regarding fluid structure interaction. And for this part, I'm going to basically pick one example and just work you through our entire workflow of how this works. So our example is we'll have a column and we have a bomb against it. What happens? More specifically, we'll know bad things happen. So we'll start out with the OpenRadioss model, and a lot of these details, I'm assuming everyone in the audience will be fairly familiar with. This was part of a bigger model, but for testing, we just extracted a single column. And in this particular case, we have hex elements, which are one of the concrete models, and we also have beam elements to model the rebar. For the concrete, we have defined each of the surface or each of the hex surfaces that are exposed as blast faces, and we have put on an erosion criteria, so this can fail as the model evolves. So if we want a fluid structure interaction, we'll use the radius for the structure, and we'll use our own code for VIPER. So what we do here, in this part, we have to set up our numerical domain and the fluid properties. So with this case, we're using about 9 million fluid cells, and our radius model has 86,000 hexes, 21,000 rebar elements, and we're going to be running this for 20 milliseconds. And everything I'm about to show you was run on my laptop, which is a typical Alienware laptop, 3080 Ti graphics card, Intel processor. And one of the really nice features of what we're doing with our FSI is VIPER is a GPU code. So all of the fluid calculations are being produced and performed on the GPU. Radius is a CPU code. So all of the finite element calculations are being produced on the CPU. So that means we are exploiting the entire computer resources, and the two codes really aren't competing for resources, allowing it to go even faster. So by exploiting both aspects, we really can make a performant code. So for the workflow, you have to use your favorite program to make your radius model. And then to get down to the VIPER model and put it in, it is a very simple process. So this is our typical input deck or typical GUI. We just click on the model we want to import. We found the import, we initialize it, and as soon as it loads, we have our model in VIPER. And we're just going to rotate around. You can see it. This is a fully interactive view on one of the other panels that we're not showing at the moment we have already defined our explosive properties. And this video is a real-time video. So it is very, very quick and efficient to load a model like this into VIPER. So now that we have a Radioss model, now that we have it imported into VIPER, we can run this thing. And we've made this reasonably simple to run. At the moment, it's a command line interface. So the coupling is also done through MPI. So it's a very simple coupling process. It's been initially developed on my Linux laptop. So we use OpenMPI, but we've also been doing a lot of testing and further performance enhancements and development on Windows, where it runs with Intel MPI. We are passing information back and forth on every single step. So we always have to pick the minimum time step between the two, and are always evolving on that time step. So the fluid and the structural response are perfectly synchronized. So in brief, OpenRadioss calculates your positions of where the element is, passes that to VIPER. VIPER calculates the forces on those elements, passes the forces back. Radioss then determines how the structure moves and responds, and then we just keep going back and forth until the simulation is done. And this communication does happen at every time step. So a lot of these details and some of the technical aspects I'll be discussing tomorrow at Silos, or you can see me later today if you want them now. And the other thing too is we are in contact with Radioss and Altair, and it is expected, or we're in the process of trying to get our the Radioss changes into both OpenRadioss and hopefully Radioss itself. So you will always have access to the most up-to-date version of OpenRadioss. You'll always be able to use the most up-to-date material models that are pulled in, or the bespoke models and all the other features that have been developed here. So you will not be stuck with just a version stuck in time. So how does this work, or how does it look? How does it perform? So before FSI, one of the main ways to model structural response, and what you can still do in a lot of cases with reasonable accuracy, is an uncoupled simulation. So in VIPER only, we can just put in the column, run the bomb against it, and the column in this case is a static column and doesn't move. And we can, because we have defined all the blast faces, we can record the pressure load on every single blast face. And on my laptop, this took 13 minutes to run. And then once we have that, we can export the pressure loads, put that into OpenRadioss, and we can run that there. And now that we have the pressure loads being applied to the column, we can see how the column responds. A lot of the concrete gets vaporized. We do have the movement and deformation of the rebar. And in Radioss, the engine runs in about 1.5 minutes. So it's very fast. Again, on my laptop, 8 CPU cores. The difference can be in the starter file, which can either run almost instantaneously or up to 9 minutes. And this is dependent on a decimation parameter that we put in. So more or less, how big is the pressure loads file you import? We have some ways to make that reasonably small. And in the 0.16 second or 0.16 minute run, I think it was about a 60 meg file. And that was able to get rid of a lot of pressure loads and just allows for more interpolation. If you don't want any interpolation and have the complete pressure load set, and it was about a 5 gig data file, which took about 9 minutes to load into OpenRadioss. So depending on how you choose to develop that file will depend on the starter time. Won't really have much of an impact on the engine. But this means that to run this fully uncoupled simulation, it takes about anywhere between 16 and 22 minutes. Or we can run a fully coupled simulation, and on my laptop, it just took 28 minutes to run. So this is, and this is equivalent to the longer starter time, because we are passing information back and forth. We're not doing any decimation. We don't have any assumptions on interpolation. So this is more akin to the 23-minute time run, and we can do the fully coupled simulation in 28 minutes. And we can see how well the fluid reacts and how well the column gets destroyed. And just a couple slides showing you the response. In general, for this particular example, the results are reasonably similar, but this is what you would expect for this particular problem. But we can see that there is a lot more damage in the uncoupled, slightly more damage in the uncoupled model than the fully coupled model. But again, as expected, because in the uncoupled model, all the pressure loads are assuming a fully static model, whereas in coupled, we can have some venting. They can move around where fluid elements used to be. So it does mitigate a little bit of the damage. And we can also see in both cases the deformation of the rebar. So even though VIPER itself does not model or really care about the rebar, because it is fully integrated into the OpenRadioss model, it does get the deformation as you would expect. And in both cases, the deformation of the rebar follows along with the full destruction of the column as you would expect. And some of the differences can be a little bit more visible on the side-on model, where again, we definitely see some more damage on the uncoupled model. So that is our current progress on our fully coupled simulations. And again, if you have any questions throughout today or the rest of Silos, please feel free to talk to one of us about it. And now I want to move on to the third section, where I'll highlight and introduce to you VIPER Sidewinder, which is our in-house native post-processor. So the main aspect that should hopefully catch your attention is this will be a free tool. We're not making it open source, but we are going to be providing it to you for free. If you are interested in obtaining a copy of this, please see myself or one of my colleagues, and we'll get you on the list. We do expect to be able to put this out and release in the next month or so. So please feel free to ask us about this. The original intent of this was to help new VIPER customers with the post-processing. Because prior to this, we were using we're using ParaView, which is a very nice and very powerful post-processor, as you all know, but there is a bit of a steep learning curve. And if you are not necessarily as computer literate as some of our clients may be, then it seems like we're spending a lot more time trying to introduce and instruct ParaView as opposed to VIPER and the actual physics. So that was the intent behind the developing of Sidewinder. It was also initially designed to fully read VIPER output files and work with that. But again, very important to this audience is we have a now feature where we can natively read the Radioss animation files. So normally with ParaView, you have to convert from animation to BTK, then read in the BTK and hope you don't max out your hard drive, which I've done too many times. But with Sidewinder, it just automatically does that in the background. There's no conversion external that you have to do, no extra files that are generated. So this does enable a fairly easy workflow for either a purely fluid simulation or also a very easy workflow for a fully FSI simulation. So this is a static image of our interface of Sidewinder. It is a very simplified user UI. It should be intuitive and easy to use. It's fast and responsive. And again, right now it's been currently optimized for VIPER Blast and for OpenRadioss. For the more technically minded or technically curious, it is based in .NET Avalonia. It is cross-platform, so it does work on both my Linux laptop and on a standard Windows computer. It has been primarily developed on Windows for those clients. .NET is open source, it is high performant. And again, we have all the BTK libraries. That is the typical output for VIPER. It's good for visualization and rendering. There's a lot of support for it and so forth. And we have already built in a lot of capabilities for this. So we have, we're easily able to model points, which in VIPER is typically tracers of the burn products. We can render volumes quite nicely, obstacles and cross sections. And again, in the bottom corner, we have the radius finite elements, and that is directly from the animation files. So all of these are directly put into Sidewinder. Also similar properties that we have from ParaView is, again, we can interrogate individual points, we can interrogate individual cells, so you can get all the data that is there. And we also have some line plot capabilities. So if you want to know about your time histories, we can easily read those in and map those out, so you don't need to either fight with ParaView to get that or use your other favorite line plotter program. We also have designed for that these things can be scalable, that can be offset. So there is a lot of flexibility with this. And I'm assuming most people only have a few dozen gauges, but we have tested this and we can actually support up to and over 100,000 lines. It does slow things down, but we have that full capability. It is also ultra fast, again, fairly easily to use. We can see here in this video how easily you can turn on and off different features, how we can just rotate and all this ability. So it doesn't have all the full capability of ParaView, but that was the intent of writing it. So it has all of the most important features for the fluid community and probably even you guys yourself. If there is another feature you're interested in, you can always talk to one of us and we can see if it's compatible and worthwhile, and if it would mesh with what we're doing. But it is a very good and very useful feature. And I already highlighted this one before, but this is the video made from Sidewinder for that column example. And you can very easily see how well it does. So this is a very nice post-processor that we have developed. And for the last little bit, I appear to be writing faster than I expected, but I have a bonus demonstration for you that a few people might have seen already on LinkedIn or last night. So to demonstrate some of our full capabilities with our FSI, we really wanted to push it to the limits, in part to see how well we can do, to make sure that the code works, and because we want to make really awesome videos. So because we're coupling with OpenRadioss, we figured why not help do something that they've done. So I'm assuming a lot of people will recognize this car. It is the input deck that we took directly from the OpenRadioss website. Now, when you use their input deck as is, the car slides into a wall, crumples, and gets destroyed. So that's kind of fun. I think that was the first model I actually ran with OpenRadioss. It is quite a big model. You got about, what, 3,000 hexes, but you do have over 1 million quadrilateral shells, which also means we have just over 1 million initial blast faces. So this is quite a big model, so it will be really good to test. But we're in the blast field, so I really don't care what happens when it hits the wall. I want to know what happens when it parks over an IED. So if you have, in this case, a generalized explosive, apparently I was a little bit ambitious and made it 12.5 kilograms. What happens to your car? So this is a render of our car actually taken from VIPER. So we imported the car into VIPER just as I showed you with the example of the column. This is our render. So because we work on a fluid grid or regular grid, cells are either blocked off or not blocked off, depending on where the car is. So this is what VIPER sees. And we want to run the car and see how bad of a day you're actually having. So short story, you do not want to be sitting in that car. Long story, awesome explosion, or awesome video. The other fun aspect or useful aspect is this turned out to be a very, very useful test case for development. And again, I believe my colleague made this video in Sidewinder. So we do have a lot of capabilities with that. So just to summarize what I've been talking about today is we have developed a fully coupled FSI code that couples the GPU power of VIPER and the CPU power of OpenRadioss. We're going to have the OpenRadioss aspects of our coupling fully integrated into the OpenRadioss and Radius at some point in the near future, we hope. We have developed this post-processor, which again, we'll be giving away for free. So if you want a copy, please feel free to contact myself or my colleague about that. And with that, I would like to thank you very much for your time, and I'll answer any questions you may have.